Welcome to the second section of the third lecture of Chemistry in the Kitchen. Let's pick up our discussion of milk composition with the topic of milk homogenization. It's been estimated that there are greater than 1 trillion fat globules in a liter of milk, and these globules come in a range of sizes from 1 to 40 microns, which is a very small size. So small, in fact, that we wouldn't expect, based on laws of physics, that these particles should cream rapidly. Now, we all know what creaming of fresh milk is, even though we probably haven't all experienced it personally. And that is the phenomenon that if we take a bowl of fresh milk and set it on the countertop for a couple of hours, it quickly separates into a cream layer on the top and a milk layer on the bottom. Why does this happen? Well, we can think about it in terms of Stokes' law, which will describe the force that's required for that dispersed phase to separate from the continuous phase. And we see this formula here, and it's not a terribly complicated formula, but let's simplify it to say that the force depends on the radius of the particle size and the velocity of the particle. And the velocity really hinges on the difference in the viscosity between the continuous and dispersed phases. Suffice it to say that at this particle size and these viscosities, we shouldn't expect creaming to occur. Well, why does it occur? And more importantly, how can we combat it in a commercial situation? Remember that your milk is homogenized, and what that means is that we don't see separation on the refrigerator time scale. Why does it happen? Well, let's turn to the proteins that are present in milk to think about how creaming happens and how we can combat it. First protein to think about is called macroglobulin. This is an immunoglobulin that's a really effective cross-linker of particles, and it's interacting with the surface of that fat globule mostly through the proteins that are attached to that surface. Remember that the fat globule is a oily triglyceride core coated with emulsifier molecules that are derived from the surface of the cell that the drop buds from. Well, this macroglobulin effectively creates particle sizes of 800 microns or more because of this cross-linking effect. Now, that is an order of magnitude or greater than the sizes of the raw milk particles, and so the cream readily separates from the milk. Homogenization counters this in a couple of different ways. But first, let's think of the particle size. Let's look at the upper right here. We see a figure of a milk homogenizer, and the way it works is simply to force the milk through a small aperture at high pressure. This creates a very homogeneous dispersion of particle size, small particle sizes, relatively narrow range of particle sizes, effectively increasing the surface area of the fat globules by quite a bit. And what this allows is the interaction of the fat globules with another whey proteins, the caseins, that accrete on the surface of the fat globules. And in this case, we're not cross-linking, we're actually screening the fat globules from cross-linking and aggregation, and therefore creaming. Another way that we can combat creaming is to denature macroglobulin. Remember what denaturation is. This is the unfolding of proteins. Well, pasteurization, as we'll see, is heating the milk to various temperatures, as we'll see, and we know that heat is one way to unfold or denature proteins. So the denatured macroglobulin no longer serves as a cross-linker, and therefore doesn't aggregate those globules to the larger sizes. Okay, now the figure on the bottom right is a complicated one, but it's kind of fun. It's derived from this paper back from 1966, Journal of Dairy Science. This is a fat globule not interacting with other fat globules, but with bacteria. It's only to show you how the cross-linking works. The bacteria are being cross-linked to the fat globule through macroglobulin that's present in the solution. So the bacteria, these is from the Brucella genus, are serving as a proxy for our purposes for other fat globules. So we see that the attachment of the bacteria to the surface of the fat globule, mediated again by immunoglobulins that we can kill by heat denaturation. All right. Here's a nice table of milk proteins. Let's think about them as casein proteins and whey proteins. This is a bit of an arbitrary distinction. Whey is usually just referred to as the solution that's left behind when milk curdles, and we'll have more precise definitions later on. But essentially, the caseins are molecules. These are the molecules that actually do precipitate out and form the cheese curds when we make cheese and other products I'll talk about later. You can look at the grams per liter. The main thing to note here is that the caseins in general make up the lion's share of the protein composition of milk, and they come in three basic flavors, alpha, beta, and gamma, and that's going to be important in a few minutes. For now, I'll just say that together, these three casein molecules form a very complicated and massive structure called a casein micelle. So remember micelles, we've talked about them before in the context of lipids and how lipids aggregate together to avoid exposure of their oily surfaces to the aqueous environment. Same thing is happening here. The caseins are aggregating and forming this enormous cluster and exposing the hydrophilic portions of the molecule to the aqueous environment. Gamma casein has some interesting characteristics, and we'll talk about those in a moment. But for now, yes, three caseins, one big set of casein globules. The whey proteins are much less, a much smaller component of the milk, at least in terms of mass. Some of the, I've listed lactalbumin and lactoglobulin here. The functions of these are less clear than the immunoglobulins. I already mentioned one immunoglobulin, macroglobulin, and its role in creaming of milk. There are other immunoglobulins present as well, and it's well documented that one of the roles of milk is to provide some immunoprotection to the infant that's consuming the milk, and this has been demonstrated a number of ways. Any of you are interested in the power of breast milk to give some immunoprotection to the infant, please contact me and I can give you some resources for that. Anyway, it makes perfect sense that the milk would be packed with not only nutrients for the growing infant, but also for some protection. All right, caseins and whey proteins. Let's focus on caseins first. So this is a figure derived from food, the chemistry of its components. It's a great figure. It's just one model of how the casein micelle works. There are many models, and part of the reason is that this is a fairly disordered complex and hard to understand structurally, but this gives us a flavor of how the caseins work. So we have complex aggregates of the alpha, beta, and kappa caseins, and we see that here. And we see how those proteins might aggregate into large micelles with the oily or hydrophobic parts of the molecule all interacting with each other on the interior, and the hydrophilic or water-loving portions of the molecule exposed to the surface. These P's represent phosphoryl groups. Phosphate is a highly charged ion and therefore very hydrophilic, so those pepper the surface of the molecule, making it more soluble. Those are on the surface of alpha and beta caseins. Important to note that kappa casein is covered with a trisaccharide tail. For the protein chemists in the audience, the trisaccharides are attached at near the C-terminal end of the molecule. The alpha and beta caseins bind calcium phosphate. This is important, and I'll come back to this again in a moment. The bind calcium phosphate, and that helps link these small particles into much larger particles, and ultimately what we get is this very large scale micelle in which kappa casein, the highly charged and highly hydrophilic casein, is exposed on the exterior, and its presence is limited on the interior. Now, okay, so the two things to note. Again, we form this very large micellar structure, the surface of which is coated with carbohydrates and negative charges. But the internal structure is composed of smaller aggregates linked together with calcium phosphate, so-called colloidal calcium phosphate. This is a really important point because the calcium composition, or the calcium content of milk, is much higher than it should be based on calcium solubility in water. And what the casein micelles actually do is increase the calcium solubility dramatically, and that's a really elegant solution to a biological need. The growing organism has to lay down bone tissue, and efficient way to do that is to increase the amount of calcium that we can deliver in a small volume. So milk is a really, again, what I would refer to as a really elegant biological solution. Okay, casein micelles. These are gonna play a really important role in several processes, so let's keep those in our minds. Coagulation, and here are those roles. So let's look first at the bottom. There are three pictures here. These are also from your textbook. On the left side, we just simply see milk, which is an emulsion again of these fat globules, stabilized perhaps by casein, these hairy casein micelles adhering to the surface, preventing them from aggregating and separating. And we see this nice smooth dispersion. And here in the middle, we see, well, I've labeled this lactic acid. So under certain conditions, acid conditions increase, and the micelles dissolve in a way that I'll discuss in a moment. But then once they've become denatured, they can then, of course, what? Aggregate, right? Denatured proteins in concentrated solutions aggregate and form large-scale networks, and those we saw how important those were for egg foams, and this will continue to be very important to us. In lactic acid, we form a very diffuse network, and we'll see how that plays out in terms of food products in a moment. The third case is one that we'll have to store in our minds until we come back to cheese making later. In this case, the milk has been exposed to an enzyme known as rennet, which originally was derived from calf stomachs, and that's a really important point. The rennet is an enzyme that partially degrades the hairy casein micelle, in fact acting on capecasein, chopping off that C-terminal glycopeptide tail, and which prevents those casein micelles from interacting with one another. Once it's gone, though, the casein molecules are not completely denatured, but are perfectly happy forming long-range aggregates, and that causes the formation of these really nice, firm, stable networks that are important for the consistency of cheese. So let's reiterate. The capecasein's polar tail keeps the casein micelles from aggregating. So that's a trisaccharide, as I said. It's an interesting point to note that lots of proteins, especially in mammalian systems, are heavily modified with carbohydrates. There's also acidic side chains or functional groups on that protein, and there's a high amount of negative charge at physiological pH. Okay, no aggregation. Thank you, capecasein. Aggregation results from a variety of stresses. pH is an important one, and we'll talk about lactic fermentation in a moment, but the bottom line is when we acidify the solution, the charges on those casein molecules are neutralized. Also, the proteins start to denature, and the molecules can then form these large-scale aggregates. Also, the pH dissolves those colloidal calcium phosphates, and that also disrupts the micellar structure. I remind you that the calcium plays an important role in holding those casein micelles together. And again, enzymes that we add to the milk can disrupt the structure of the casein micelles as well. Again, protein coagulation, really important in so much of cooking. Let's talk again about oil and water emulsions. We went through this in the first part of the lecture, and all I'm going to show you here is a couple of different pictures of what happens when we homogenize milk. Let's look at the heavy cream. Again, reminding you that we have a wide range of particle sizes, and those particle sizes will only get greater as the milk sits. But if we homogenize the milk, here we see at the top, whole milk homogenized, small particle size, and we don't see as much creaming. Okay. Here I want to mention pasteurization. There are several flavors of pasteurization. These are outlined in your text on page 22. Everything from relatively gentle heating for a long period to very high heating, boiling basically for a long period. All of this cooking can affect the flavor and coloration of the milk, and so it's worthwhile pointing out that the longer and higher temperatures we treat the milk, the more the structure of the milk is changed, and this has a lot to do with the protein content of the milk. And again, I'll refer you to Maillard reactions. This is something that I have alluded to a couple of times, and we'll continue to talk about it in detail in later lectures. Most important for us maybe are the high temperature short time pasteurization, 161 degrees Fahrenheit for 20 seconds, and the ultra high temperature, which is 250 degrees for anywhere from almost instantaneous to a couple of seconds. Each of these treatments stabilizes the milk to degradation for different periods of time, and I'll refer you back to your text for that. Looking quickly at the types of cream that are available, I've given you a table here with the U.S. nomenclature versus European nomenclature, and we're just seeing the fat content increasing from half and half at 10 to 18% to plastic cream at 65 to 85%. Plastic cream is a very firm but still pourable and malleable cream, very high fat content. Europe has a different set that they utilize and different names for these, but we still are talking about a range of fat content and different applications for each of these. It's worth noting that creme fraiche and clotted cream are usually somewhat fermented, and none of the U.S. Creams that at least that I'm showing on this table have undergone fermentation. I want to talk a little bit about the different ways that we use cream. Whipped cream is something that's probably familiar to most of us, and again, we come back to what happens at the interface of air and the milk product. We saw this last week with eggs. We see similar stuff happening, although now we're mostly talking about fat. So again, fat content of heavy cream is very high, and these globules, remember that the fat globules are oily droplets of triglyceride coated with protein and emulsifying lipids that keep them soluble in water. Well, these fat globules are fairly delicate, and mechanical stress will disrupt them. And what happens then? Well, now we no longer are emulsified, and those triglycerides settle out at the air-water interface that's introduced by those bubbles, and they crystallize, they solidify. So that's what provides the structure and the stabilizing structure of whipped cream. We'll talk about butter as well. Ice cream is also worth mentioning. Here's another picture from your text. Ice cream is all about the texture. Now, what we still see is air is beaten into the mixture, and the fat globules accrete around those air pockets. There's also water present, obviously, and that's important, and the water begins to freeze and crystallize, although we're working at sugar concentrations that keep much of the water liquid, which is also going to be important for the texture. So we introduce these air bubbles and disrupt fat globules, and the fat accretes around those air cells, stabilizing that long scale structure. Okay, and again, the fat stabilizes the foam. Something that I haven't mentioned on this slide is that the importance of keeping your ice crystals small. This impacts the texture of the ice cream very dramatically, and we'll talk in subsequent lectures about the use of other kinds of additives to alter the texture of ice cream. But for now, we like to say that if we can form a small and consistently sized ice crystals, we're going to wind up with a smoother ice cream, and the texture of ice cream can be affected by the hardening process that happens after the initial crystallization, and ice crystals can grow larger and larger and make a more grainy ice cream texture. This is why I advocate the use of liquid nitrogen in preparing your ice cream. Many small ice crystals form, and they form very readily and quickly. Okay, butter. I mentioned before that most emulsions that we encounter in the kitchen are oil and water emulsions. That is, the oil is the dispersed phase and the water is the continuous phase. Butter is a counterexample. Here we can age the cream at fairly low temperatures, and this begins the crystallization of the butter fat, the triglycerides that make up the core of those fat globules. Crystallization disrupts those fat globules, and that spills the fat out into the solution, and we can form the water becomes less and less of a continuous phase, and then separates away from this more or less continuous mass of crystallizing fat and becomes the dispersed phase. Now, I mentioned that butter can be made with or without culturing with lactobacillus. We're going to talk about the role of bacteria in milk products in a moment. Historically, this is more important, less important nowadays with commercial manufacturing, but can be important for the flavor of your butter. There's also mechanical stress that continues to disrupt fat globules, and all of these broken fat globules again spill out and make a continuous phase of fat. Now, what's buttermilk? Well, again, that water has separated out and can be poured off of the butter, and very high content of, still has fat globules, lots of protein, lots of those emulsifying lipids, and that's real buttermilk. And again, that real buttermilk has often been slightly fermented, and that confers a particular flavor. It's also worth mentioning color of butter. Remember that milk is white, and I explained why milk is white in the previous lecture. These particles scatter light of a wide range of visible wavelengths, resulting in a white or opaque appearance. But there are colored molecules in the butter fat. Remember that vitamin A and beta carotene, these are fat-soluble molecules, and when we disrupt the fat globules and create this continuous phase of fat, then the color can be observed. And that's why, especially in butter derived from milk that's derived from animals fed on grass, we might have an intensely colored butter. But just like eggs now, the feed is often very controlled in a dairy herd, and so any coloration in the butter is either added directly to the feed or perhaps added later in the butter manufacturing process. But still, depending on beta carotene. But it is very interesting to see that you can go from a white, opaque milk to a nice yellow butter, and I encourage you to try this on your own.